So this lecture is about Berkovich spaces, which topic which I kind of began discussing last time, and so well, let me remind you kind of the classical setup. You have a Banach ring. So it's a ring equipped with a norm which is submultiplicative, satisfies a triangle inequality. Maybe I'll do it better this time. Norm of 1 is equal to 0 or 1, unless r equals 0, and r is complete.
And also, of course, minus x now is equal to x in order that the norm is defined a matrix.
Okay, yes. Yeah. Okay. And then to this, Berkovich assigns a compact Hausdorff space. M R norm, which is a subset over the product over all elements in R of the closed interval from 0 to the norm of f. And it's the set of all, the notation will be that a point in here will be denoted x, but what it literally is a valuation, a map from R to the non-negative real numbers, which is now multiplicative. So and again satisfies triangle inequality.
And now 1 is equal to 1.
Yeah, now it's kind of it's strictly multiplicative. Yeah, so yeah, you know, R is not complete with respect to this norm x. In fact, there could be many elements of norm 0, but so remark, if you complete R with respect to any norm x, you get a complete valued field. So kx hat, I don't know, which is sort of the residue field in the sense of Berkovich's theory. And recall that there's basically kind of 3 cases. One is Archimedean. So and that's the same thing by Ostrovsky as saying it's either R or C. So in the Archimedean case, there's no variety really in complete normed fields.
R or C, but the norm could be a power to the alpha at
yes,
plus 1.
Yes, exactly.
Bigger than 0.
Yes, yes. The second is it's non-Archimedean, but discrete. And then you have the trivial norm, so and then the third case is it's an honest non-Archimedean field, non-discrete. I mean the induced topology on the field, is non-discrete. The value could come from a discrete valuation. And then again, so you could have some normalized version. If you choose a...
Because non-discrete, there is an ambiguity.
Yes.
Yeah. It's not. It's not about discrete valuation.
Non-discrete, exactly. That was the parenthetical comment I was making. A non-discrete topology.
It depends if you call a discrete field a non-Archimedean field. I think not. But
you wouldn't even call this a non-Archimedean field. Yeah. Okay. So the norm is not maybe that. Yeah.
It's not what people call non-Archimedean.
Yeah, okay. The norm is non-Archimedean, but the field is discrete. So yeah, it's just a discrete field. So anyway, these are the three kind of cases of possible residue field behaviors you see. Right, and then so here are the alpha. Yeah. Okay.
There is no preferred normalization. So.
No, I mean, yeah, you can choose a normalization if you fix a pseudo uniformizer. You can choose and a real number. You can choose a normalization. Yeah. Right. Okay. Yes. Yeah. So these are kind of points and. So what we're going to do now is we're going to promote this. So the goal is to promote M R norm to an analytic stack. Using the stack of norms N. So recall, so a map from an analytic stack X to N was the same thing as a certain map from P1 of X, P1X to 0 plus infinity. So N satisfying norm axioms. The most important one being multiplicativity, which you have to phrase a little carefully, but in the end, it's just multiplicativity. Okay, so and we kind of investigated the geometry of N last time. So we saw that N lies over this extended Berkovich spectrum of the integers. So. So that was this space where, so I mean, here we have a triangle inequality, the usual triangle inequality, and that's what made the difference between, like, the reason you couldn't take an arbitrary power alpha here. But I mean, if you take an arbitrary power alpha, you get something that basically behaves like a norm, but it's really only a quasi-norm, so you have to put some constant in front here.
Plus the limit, you have also the kind of the limit at infinity.
Yes, there's also the limit at infinity. Yeah, so that makes in this stack of norms, there's no triangle inequality imposed, and it turns out what you get is this non-strict triangle inequality where all powers of the usual Archimedean norm are allowed. And then also there's some kind of very strange limit point where your norm takes infinite values on natural numbers. And then you have the Archimedean ones, so two-adic absolute values, which end here in a point which has both characteristic 0 and characteristic p behavior, but where the norm of 2 equals 0. And then for the other primes p. And we also kind of saw what on the interior of these line segments, you were getting the gaseous R theory. On the interior here, you're getting the gaseous two-adic numbers. And then as you move along, the norm is changing, but the kind of, so to speak, the analytic ring is not. And Q3 and so on. And then here you have things living, you have F2 living, for example. You have things living in characteristic 2 there, living in characteristic 3 here, and here you have things living in characteristic 0. So in some sense, you can imagine that the points of this stack correspond to something like these complete valued fields, or the minimal choices of complete valued fields. Like you have real numbers, p-adic numbers, you have discrete fp, you have discrete Q. So that's kind of a substitute for the notion of multiplicative valuation. But then we still have to input our Banach ring R into the construction in order to get something non-trivial. So here's the definition. And I don't know what good notation is. I'll write it like this. So this will be an analytic stack, which will be a subset of a stack of norms cross, and then some affine analytic stack, which is just we take R with a trivial analytic ring topology. It's the trivial analytic ring structure. So by this, what I mean is that you take R is a Banach ring, so it has a topology, but you can also view it as a light condensed ring. So the
So using the topology, you consider the condensed set.
Yes. And then trivial analytic ring structure.
That is, all modules are allowed?
Yes.
Even not the, okay.
It's the full, condensed derived category of this condensed ring. So that means that if you want to give a map from X to this spec R triv, that's exactly the same thing as giving a map of condensed rings from R to the value of the structure sheaf on X. So this is going to be a subset of this product consisting of those, such that let's say maps from X to here. These are going to be by definition in bijection with. It's going to be a pair consisting of a norm. And then a map from R to the ring of functions on X, such that. And then we impose a condition. Oh, forgot to say the thing that ties this to that. So you require the multiplicative valuation to be bounded by the given norm, and that's exactly what we're going to do here. So such that for all f in R. So when you have the norm here and you have an element in O of X. You get a section of A1, and you have a section from an element of OX. You get a section of A1, and in particular a section of P1, and then you can compose with the norm, and you get a map norm F from X, X to 0 plus infinity, such that this map lands in 0 and then norm of F. Okay. I guess the first theorem would be that, so this is an analytic stack. Which localizes along the Berkovich spectrum MR. So in the sense that I discussed in the last lecture, so that if you look at this locale of all open substacks of this spec Berk R norm, this maps naturally to compact Hausdorff space, which is the Berkovich spectrum.
So you have the locale of open in the usual topology, and the locale.
Wait, usual topology. Just, oh, on the right. Yeah, on the right. Yeah.
But on the left, open substack means what? It means a monomorphism.
It means a monomorphism which is shriekable and cohomologically smooth.
And this was discussed in one of the talks. Okay.
And you could even ask for a map of analytic stacks, right? At least from.
Well, when this is finite dimensional and metrizable, yes, which is basically all cases. Okay. But I mean, yeah.
And then it would be.
Yes. Yeah. So again, so in the case when this is metrizable and finite dimensional, to verify that you have a map, I mean, it's really just a condition to say that you would get a map of analytic stacks to that thing, and it's just you have to check some connectivity properties of the idempotent algebras assigned to closed subsets that are kind of implicit in this map. So it's a condition that you can check in practice. And
so is it the case that you have, since R is cool, you can think of it as a limit of certain subrings which are generated by countably many elements?
Yes.
So you can probably reduce to the metrizable.
Yes.
No, but maybe it's not finite dimensional. Well, I'm not sure, but
no, but you can look at it as a colimit over finitely generated subrings, and that's always embedded in a finite. I mean.
Okay.
Yeah, so,
yes.
Yeah, so that's one way. So there is indeed a canonical way to write this as an inverse limit of finite dimensional metrizable spaces, but let's not do it. Let's just work with this this setup here.
And is it true that you have inverse limits in analytic stacks?
Yes, you have all limits. You have all limits in analytic stacks. Yeah.
Okay. So you can think of it as a limit over the stack as a limit over the.
Well, this isn't a stack now. This is just. I'm just viewing this as yeah.
When you have those nice subrings, you can construct. Okay. So it's not. No, but then you can take, for the nice subring, you can take the stack associated to M and take the inverse limit, and you get something which is.
Yes. You get something, yeah, but then you get something. The only problem I have with that, it's not a real problem, but just, is that if you started with something which happened to already be finite dimensional and metrizable, then you'd be non-trivially writing it as an inverse limit of other finite dimensional metrizable things. And I mean, you know, so let me just not get into it.
Okay.
Yeah, just one other question.
Yeah.
When R is state, then we also saw that we can localize over the spa.
Yes.
R. Yes. And then there's a map from the spa to the Berg. I mean.
That's right. That's right.
And so there's.
Yeah, there's a commutative there's a commutative diagram that you can write down where here you have a map from the Huber space mapping to this, and then you have this thing, and then you have the solid guy here mapping to that, and.
This last arrow, I mean,
No, yeah. When I'll discuss in more detail what this looks like in the Tate case, and then you'll see. Yeah. Okay. So in particular, just I want to highlight that we get a structure sheaf on this topological space, and even a structure sheaf of infinity categories. So a theory of quasi-coherent sheaves on the usual Berkovich space. I'll explain in basically the Tate case how it's pretty easy to calculate this structure sheaf and see what it's doing. In the case of rings like the integers, well, the integers you can kind of do it by hand, but it would be interesting to compare. So I'll explain basically how you compare to the cases Berkovich discussed, but it would be interesting to compare to Poineau, who kind of more or less by hand described structure sheaves in certain cases over the integers. So this is a different different approach where you define something which is a priori a structure sheaf and then you have to calculate it, which can be done in principle, but takes a while. In Poinot's case, he explicitly assigns the value, and then he has to maybe prove some descent results. So here we automatically get some sort of infinity descent, but then you have to calculate the value. Okay.
Basically, you do it by assigning values to, like, I don't know, disks, and that shouldn't it be easy to say what it is on a disk, the structure sheet?
Yeah, it does reduce to seeing what goes on a disk, but to see what goes on a disk, yeah. So I do believe that it. Yeah. So I'll explain what you need to do these calculations, and I think you'll see that it is like.
But probably there are, like in the case of Hooper rings, there are probably some derived phenomena.
Yes.
Because when you want to look at things like the algebra of functions on a closed or open disk. Anyway, you quotient something by certain thing. I mean, you have non-closed ideas, so probably you need to work in some derived sense to get the right to get what you get from your function theory.
Yes.
You should probably have derived rings, which are complete.
Yeah, we do. Yeah, I mean that's what. Yeah. Yeah, so I do believe that in cases like what Poinot considers, where you're starting with a discrete ring, like say the integers, that the calculations are quite feasible. But if you started with maybe a more arbitrary Banach ring, it's maybe not so obvious how to do the calculations. Okay. So where are we? Okay. I want to explain, okay, so why this is true, so I guess proof. Well, that it's an analytic stack, I mean, we defined it as a functor of points. So, I mean, the only thing to make it an analytic stack is some accessibility, but let me explain how to give charts for it. So let's give charts. So recall that we had charts for the norms, the space of norms. So we had this spec of z q hat plus or minus 1. This gaseous theory, and this we can view as the universal So it sits inside P1. It's kind of the universal locus where, say, absolute value of t is equal to 1/2. Right. So if we pull back along this, then So I mean, we look at the spec Burke, our norm, and then spec z q hat plus or minus 1 gas, and then we get this some universal disk over here, some universal, well, I don't know, annulus over here. Let me just call it y. Then, so for this y thing, we've already got the norm. We've kind of artificially adjoined an element of norm 1/2. But the only thing we need to ensure to go from this to this is we need to give the second map. We need to give the map to spec of R with a trivial thing, and we need to see that they agree. And we need to enforce the condition that this norm condition that NF lands inside that part there. So to get Y, you just take spec of Z Q hat plus or minus 1 gas cross spec R triv, and then pass to the closed subsets given by the idempotent algebras. Obtained by taking the norm F inverse of these closed subsets here. So, in other words, this y is affine. So this Berkovich spectrum here has a fairly simple cover by an affine. And to calculate this affine, the most difficult part, for like a completely general R, the most difficult part is already in the first step. That is making this product and calculating what analytic ring this is, and in particular calculating what the underlying condensed ring is. Because what this tensor product involves is you have to calculate the gaseous localization of like R, yeah. So you have to then apply this gaseous localization again. And recall from Peter's lecture where he described the gaseous localization that it's given by some sequential co-limit. There are some Koszul complexes, and it's a little, yeah. And then but once you have that, I'm gonna explain that calculating these idempotent algebras is not that hard. So once you know the ring you have here, then you're passing to certain idempotent algebras over it, and that's not the hard part of the calculation. But so in particular, if you're in a situation where you can do this calculation, then it's quite feasible to calculate y, which is giving a presentation for this stack, and we also saw that like the descent for this cover is quite simple. It happens at the 0th stage, so the structure sheaf here will just be a retract of the structure sheaf here, so the ring of functions on this y.
So what did you say, the descent?
Oh yeah, when we argued that that this map was a cover, we did it by saying that it was proper and descendable, and we even showed that like the unit object, the structure sheaf here is just a retract of the push forward of the structure sheaf there. So that makes the descent quite straightforward. Basically, when you're passing from here to y, you're adjoining some extra variable q, and it has some analytic properties, but you calculate some ring up there, and you just look at the possible 0th coefficients of that ring, and that tells you the value of the structure sheaf here.
The local ring is a direct factor of the one above.
Yes, yeah, exactly. Not as a ring, but I mean, it maps, and then there's a linear retraction. Yeah, just like if you had Laurent series, like constant coefficients inside Laurent series. Yeah, yeah.
Is it a factors modules?
Yes, exactly. Yeah. Right. Okay. So. And the map to the Berkovich spectrum is kind of so on this spec Berk, so the map to so on spec Berk, you have the universal norm. Let's call it n. And then we also have, for every element in R, we have by fiat a map to the structure sheaf here. So then we get a map from spec Berk R to product over all f in R, 0 norm of f. But since we enforce that every element of R, for every element of R, the norm of that element is bounded by the prescribed norm on our Banach ring R, that in particular implies that the norm of 2 is less than or equal to 2, which means that by last time, the triangle inequality holds. For n. And that means that this map lands in inside the Berkovich spectrum indeed. I'm sorry?
You mean the image of MR in the product?
Yeah, MR is by definition a subspace of the product, yeah.
So this construction could also teach some version of the Banach ring which does not satisfy the triangle inequality.
Right. Yeah, I mean, yeah, it's natural from the perspective of this stack of norms that we've been discussing, as we've seen, to relax the triangle inequality, and you can do that. I mean, you could. I mean, the formalism is quite general. The reason I stuck to the classical thing is just because it's the classical thing.
Placement you have for the triangle inequality. You assume that.
Yeah, you could require that there exists a constant such that you know that's one thing you could do.
Okay, but then if you want to so this still defines a uniform structure, so you can say it's complete, and it is not equivalent by changing things slightly to a actual norm if you have this, or
well, I don't know,
because for fields
it would be.
Yeah, I think if you just rescale by power, it's a usual one. So.
Is that true?
This wouldn't be as much. I mean, I think this is ROP something zero.
Maybe it's true. Yeah, yeah. But you could also conceivably allow the norm to take infinite values and try to build that into things as well. Yeah, I just wanted to stick with the classical thing.
So there is a theorem about the scaling. No, if you have a norm with the kind of, I don't know how it's called, with the constant.
Yeah.
So it's a theorem that for fields, I think, you only get the previous classification with an alpha, I think.
Yeah, yeah, I think you're right. Yeah.
But for rings, you don't know that, because it's delicate, because if y is in a small norm, this condition doesn't imply that the norm of x and norm of x plus y are close.
Yes.
So.
Yes, I agree it could be subtle for a general ring. I don't want to make any claims. I actually want to stick to the classical setting. Okay, so this was me explaining the general case. But there is, and in the general case, this thing, despite the notation with this spec, this is not going to be affine. So for general, this spec, Berk, R, is not affine. So it's not the spec of an analytic ring. So for example, well, if we look at spec Berk Z, and then the usual Archimedean absolute value, which is the kind of the maximal, every norm you could put on Z will have to be less than or equal to this one. So this is kind of the choice that gives you the biggest possible Berkovich spectrum. This is this is just this locus where absolute value of 2 is less than or equal to 2 inside this stack of norms, and it really is a stack, as you can kind of see at the points that live at the boundaries. Okay, so however, suppose, so let me make a assumption star that, so there exists, let's say, a pi in R such that norm of pi is less than 1, pi is a unit in the ring, and I want it to be that it strictly like the norm strictly multiplies when you multiply by, the norm is multiplicative with respect to multiplying by pi. So this, well, this condition is obviously not satisfied here, but it's satisfied quite broadly. So example, so any non-discrete. Yeah, I apologize again. Non-discrete, I'll put it way over here so you don't think I'm saying non-discretely valued field, but non-discrete valued field, yeah, admits such a norm.
Sometimes they say non-trivially valued field.
Okay, yeah. So you could, there you have multiplicativity for all elements, and then if it's not discretely valued, then there's something with norm between 0 and 1, and that'll be a unit, and yeah.
Of course, there is a slight ambiguity in valued field because sometimes it refers to absolute value. Sometimes to crude valuations, it could be higher rank, and then you have to say, I mean, it's not, it's here it's valued in the sense of
yes.
Real value.
Yeah, exactly.
These are the medium.
Yeah.
Okay.
Yeah. And then so if R satisfies star and phi from R to R prime which is a map in the appropriate sense, so contractive homomorphism, then R prime also satisfies. So with respect to phi of pi. Well, the reason is, you take the same pi, its image will be a unit, and it'll be, the norm will be less than 1, but also the norm will have to be the same because, this condition is equivalent to, unless maybe R is 0, I don't know, is equivalent to saying that the norm of pi inverse is actually the inverse of the norm of pi. As you can see by applying the multiplicativity, the submultiplicativity property of the norm. So then, and that condition is kind of more obviously preserved by.
Okay, so actually in the Berkovich theory, I think sometimes it's natural to consider homomorphisms which are not, the norm is on the phi of x is less than or equal to, let's say, a constant at the norm of x. This defines still a map on Berkovich spaces.
Yes.
I suppose that your definition does not depend. That is, if let's say you have two norms which are equivalent in this sense by constants, then all of this will be the same for the two norms, I suppose. But
well,
one is to say something.
Not quite. So I mean, let me say what I can say, and then sorry, I just okay.
I think it is true.
Was that
get past power to pi? So
yeah, but in under this assumption you mean, or in general?
I would say this. I think this assumption is somehow invariant.
Yeah. I agree with that. So that's why I want to postpone the discussion. A bit. Okay. So in particular, I mean, the classical settings in Berkovich geometry, you work over some fixed field, which is often non-discrete, and and you're working with Banach algebras over that field, and they will certainly satisfy this condition star. But if you're working over a discrete ring, you won't have this condition star. So then I claim. Well, let me give it. Yeah, well, we're also So also any Tate-Huber ring has a norm defining the topology satisfying star with pi a pseudo-uniformizer. So also some mixed characteristic examples exist. Right. So where am I? So then claim. So if star holds, then spec Berkovich R norm is affine and corresponds to an analytic ring structure on the condensed ring R. So moreover, this analytic ring structure only depends on the condensed ring R, not on the norm, satisfying star. Yeah, so I hope in some sense I'll be addressing your question. I mean,
no, but I think that just from your definition, if you have two equivalent norms, then you by constants, that's the simplest case, then you just look at the condition you impose, apply to.
Oh yes. Yeah, I think you're right. Yes.
So similarly for a morphism of rings, if it is only with a constant, you could still apply the same thing, get a morphism of stuff.
I think you're right, Ofer, yeah.
So this, because in some, I remember that in some texts, I don't know if the book of Berkovich, in some place they consider such things, which is more, apparently more natural, because I don't know the why, but it's probably you can't.
I think you're right that because our norms are by definition multiplicative. I mean these geometric norms that you can argue exactly as you suggested. Yeah. Yes, that's a good point. Thanks. Okay. Right. So what doesn't depend on what depends on more than R? Well, on this thing, you have this universal norm n. So the universal norm n on spec Berk R does depend on the norm you choose on R. But any two choices are equivalent under, so norm passes to norm to the alpha. So for some map alpha from spec, oh boy. Sorry, let me continue over here. And I could remove the second factor from the notation here, because as I said, the stack itself only depends on R. But okay, I'll keep it. So there's what I'm referring to here is there's a scaling action. So I'm referring to the fact that there's there's a scaling action which sends a norm and a continuous function alpha to the norm. You take the norm and you compose with the alpha map on exponentiation map on 0 infinity, exponentiation by alpha on 0 infinity.
So here you wrote spec. No, I'm so. What was the notation for the classical Berkov spectrum? Is M of R? R.
M, yeah, M.
Okay.
Yeah.
So the alpha is a map to positive reals, but does it factorize through M of R, or what is it? Is it? No.
It does, right?
Okay.
No?
That it wouldn't surprise me if it did. It's just the argument I prepared doesn't quite show that. But probably if you look more closely, it will. Let's give the argument and then maybe try to address the question. I'm going to give the proof of this, and then maybe it'll be easier for us to answer the question after having seen the proof. I'm not claiming it right now, but I'll give the proof for this claim, and then maybe at that point we'll be able to...
Of course, you can just change the norm on R itself by taking a power, and then this will be the alpha. If you just change the norm by a power,
yeah.
If you change the norm by a constant, then what I said before, this doesn't change.
Yeah.
But if you change it by raising to a power, then you probably this alpha will be constant.
Yes.
But it doesn't.
No, I mean, so the thing is, like, there's two choices we need to take account for. One is that, like, a choice. Well, let me give the proof, and then we'll be better equipped to try to answer questions such as these. Okay. Okay, so the proof, I'm going to explain how to produce this analytic ring structure on the condensed ring R. So take pi as in star. Then we get a map from ZQ to the condensed ring R, which sends Q to pi. But pi is of norm less than 1, which implies that it's topologically nilpotent. So its sequence of powers tend to 0. That implies that it factors through this ring here. And it's also a unit by assumption. So we get a factoring through this ring here. And then, we need to check, or we want to check, that R is gaseous, Q gaseous, as so recall that this gaseous theory was a non-trivial analytic ring structure, which was produced by taking, by realizing that the category as a full subcategory of modules over this ring, and then there's this completion procedure which changes the underlying ring to this gaseous thing, but the category of modules was just described at this level. And this is something very straightforward, because the definition of gaseous was that some map from P to P, P being the universal null sequence, so to speak, namely 1 minus T times Q, should be an isomorphism on maps to R. But when you map out to R from this null sequence space to your Banach space, you're just getting the space of null sequences in the Banach space. So that's equivalent to saying that if you look at the space of null sequences in R, and then you have some 1 minus Q times shift that this should be an isomorphism of condensed, well, of Banach abelian groups, say. But this is, but it's easy to see what the inverse is supposed to be, and to write it down, you need to just, you need that if sort of Fn is a null sequence, then you can sum Fn pi to the n and still get an element in R. The condition on pi is, and the usual triangle inequality stuff lets you write this down. It's just the limit of the Cauchy sequence. So it's quite straightforward to check that R is liquid, and then we can just take the induced analytic ring structure. So, what's that? What? Oh, I keep saying liquid instead of gaseous. Yeah, it is liquid. Well, anyway, it's gaseous. Take induced analytic ring structure from Z, Q plus or minus 1 gaseous. So now recall that on spec of Z Q hat plus or minus 1 gaseous, we have a universal norm with the norm of pi strictly equal to this. Okay, now maybe let me say R is not the zero ring. If it's the zero ring, I leave the claim as an exercise. So then if it's not the zero ring, then this pi will have to have norm bigger than 0 and less than 1. And then on this, we have the universal norm where the norm of pi lands inside this singleton subspace. Maybe I'll write it like that to remind you that this is kind of a subset and not a value. Right, and then we can then by functoriality of norms, because norms pull back, we get a norm on
What is pi?
What?
Q.
Pi.
Pi is Q.
Pi is we're fixing one of these guys, which exists by hypothesis.
No, the other pi is for the
What?
It's a Q, I think.
Q? Oh, thank you. I'm sorry. Yes, thank you. Yeah. Right. So we get norm on R with induced analytic ring structure. And the claim, so this normed analytic ring is spec Burke R with respect to this norm.
Represents.
I'm sorry?
Represents.
Yeah, represents is, yeah. It's the same thing, right? All right.
Well, we got the count from algebra to geometry.
Okay, spec of this. Okay, so what does one need to do to prove this claim? So what have we done? So, well, maybe I need a name for this normed analytic ring. Let me call it R liquid.
Yes.
R gaseous. Although so far I haven't shown that it's independent of the norm on R, but we'll see that in just a sec. But let me hide that in the notation. Right. Where am I? Oh yeah. So far. So what have we? So over spec R gas, we have the map to spec R triv, and we have the norm n with norm of pi exactly equal to the singleton value pi. And it's easy to see just by tracing through the construction that this is universal with respect to that. Or with respect to that structure. So what's the difference with the thing we're trying to compare to? It's that instead of having a condition on just the norm of pi, which we have here, we have a condition on the norm of every element. So we need that this condition on a norm is equivalent to the condition that norm of f is contained in 0f for all f in R. So we need this equivalence. Okay, so one direction is quite easy. So if you have, so this is easy. So if you have this, then you apply it to pi and to pi inverse, and you deduce that. So the key is to see that just telling you what the norm of pi is, then I know I've constrained the norm of every element in our Banach ring. So for and also for the other, oh well, sorry, that's ambiguous, right? So yeah. So for that direction, and because it's good to know, we will calculate. So to calculate this universal norm. So more precisely, so what is a normed analytic ring structure? Recall that it amounts to specifying some idempotent algebras over P1. So we'll calculate the algebras. So for all 0 less than C. So a norm in our sense on an analytic ring is implicitly just telling you what the over-convergent functions are on a disk of arbitrary radius centered around the origin. Yeah, so we just have to specify this. And my claim is it's going to be the usual thing from Berkovich theory. So claim, so this is equal to filtered colimit of, let's say, yeah, radius bigger than C of, you take the, so I'll explain what this is afterwards, but kind of, you can make a universal Banach ring where the norm is less than or equal to R.
Is this local or global now?
I'm sorry?
Is this local or global now?
Could you make your question more precise?
I don't know if I have finite time. How much time do you want?
Well, you take the time you need, and when it's precise, ask again. Yeah.
Okay, so this is like the formal series that is when you replace each coefficient by the absolute value and replace t by r, it converges. The sum is finite.
Yeah. So this is the set of well, it's just the coefficients, but let's say Rn Tn such that some absolute value Rn. Oh boy, I shouldn't use R. Let me use F. I was using F for elements in my Banach ring. So. And then this is the norm. So this is the on. Wait, sorry. Yeah. No, yeah, that's right. Okay. So I was also making claims last lecture about calculations of what these overconvergent functions were in various cases. So I'd like to explain how to make these calculations. And it turns out there's a trick where you really don't have to do anything. It's just kind of purely formal. So there's a trick to calculating.
Of course, this is in the condensed now. You have to view this as a condensed.
Yeah, this is Banach, and then it's so it's condensed.
Okay,
Yeah.
Yeah.
And then this filtered colimit is taking place in the condensed category. Yeah. Oh yeah. So what is it we need to calculate? What is it that we're calculating here actually? So what we're doing is we're trying to calculate. We have the universal thing over this gaseous space, which we more or less wrote down. And then we have to tensor it with the gaseous tensor product, so over this analytic ring with R, where here Q goes to pi. And we have to, actually, a priori it's a derived tensor product, but this is the kind of thing we need to do. And if we're being too naive about it, it can look kind of tricky. Because naively what you do is you write this as we've explained, as some filtered colimit over copies of P. So that's kind of overconvergence. And then you'd first calculate P tensor R, and then you'd pass to the filtered colimit. But actually, it's not so easy to unwind what P tensor R is. In particular, it's not so easy to see that it would be concentrated in degree 0. So let's use a trick. So let's not use this approach. That was how we produced this thing in the universal case. So recall the idea was that this P was some version of functions on the open unit disk. And then when you have this Q and maybe all of its fractional powers, you could scale that open unit disk and get some version of functions on an arbitrary disk. And it wasn't the correct one, but when you make it overconvergent, it doesn't matter. It'll be by some kind of sandwiching argument. Okay. Right, so a trick to calculate is some general category theory fact. So lemma is, so C symmetric monoidal, let's say infinity category, it's not too relevant. But then, so if you have a tower, so x1, x2, x3 in C, where each map is trace class. So x to y is trace class, means it comes from a map so from the unit to x dual tensor y. Where x dual, I'm not assuming x is dualizable. This is just the internal Hom from x to 1. Sorry? Yes, closed. Thank you. There's probably a way to, well, never mind. Where are we? Then for all y in C, we can calculate the colimit over n of xn dual tensor y. So we have a tower here, we pass to the dual thing, which gives a sequence, and we take the colimit over that sequence. Then this is the same thing as colimit over n of the internal Hom from xn to y. So this is elementary. I'll leave it just like that without giving the proof. You just have two systems, and you make two in systems, and you make maps backwards that go up a step using the trace class hypothesis. Okay.
So again, how do you know there is the limit makes sense?
Okay, well, this is actually an equality of ind objects. So, I mean, it's an equality of ind objects. It doesn't matter.
Okay, as ind object, and you have to know what is the ind for. This is ind for C. In ind C, which makes sense as an infinity. Yeah. Okay.
Yeah, so in particular, if C has colimits, you can remove the quotation marks. If C has colimits and tensor product commutes with colimits, which is the case in our examples, then you can remove yeah, okay. Right. Okay, so yeah, so what we're going to do, so yeah, in particular, well, yeah, so what we're going to do is we're going to recognize, so if you take y equals the unit, then, you know, and yeah, this object here is colimit of the internal Hom.
Can I ask a technical question?
Yes.
About the definition. It's nice, but what do you mean by comes from a map? It's that the Hom is given by this? Or?
Right. So if you're given a map like this, then you can tensor it with x. You get a map from x to x tensor x dual tensor y, and x tensor x dual has an evaluation map to the unit. So you then get a map from x to y. Yeah. Yeah. Right. So we'll recognize C as a colimit over now P duals, and apply this with trace class transition maps. So once we do that, then we reduce to looking at null sequences in R again, and then just some filtered colimit of some space of null sequences in R, and you could actually modify this to the thing where you require these to form a null sequence, and they wouldn't be the same at each term, but it's quite easy to be they're the same when you take the filtered colimit. Again, any two versions of the unit disk are kind of the same after you make them over-convergent. Yeah, and then the calculation is very easy once you do this. And for this, for that we can use Serre duality. On P1. So it happens to be over the liquid base, but the gaseous base, but it doesn't much matter. So Serre duality on P1, and the sixth functor formalism. So Serre duality on P1 implies that so we have this proper map to the base. And algebraic Serre duality implies that this map is smooth and proper, and that the dualizing object is just this omega 1 shifted by 1. And then you can calculate then it's easy to do calculations, and I'll just tell you what the conclusion is. The conclusion is that if you take the dual of the this identifies with the ring of functions on the open complement. So
so the dual of, in the sense of
a linear dual in the category. So this is dual in there. I'm sorry? So this is an object in this category, which implicitly there's an underlying condensed abelian group and so on. So yeah.
Do you know that you deal with objects which are sufficiently finite so that like their double dual is themselves?
Right, so you need to, right, so we would want to put the dual on the other side, but we can do it with a trick more or less, because so this gives also, so this by the overconvergence, you get that the single dual of the ind object. Sorry. We can write this. This is a pro object. We can view this overconvergent thing as an ind object, and its dual will be a pro object, and it will be the pro object given by this thing where you increase the radius as well. But then now we can view that pro object as an inverse limit of the overconvergent things with the non-strict inequalities over there, and then use the duality result in this direction on each of those, and so there's some trick with overconvergence. This implies that if you take the dual of this, so if you view this as a pro object, because it's an inverse limit of the things where you have a greater than, then the dual of that pro object is the ind object that we're interested in. Yeah. And that gives an expression exactly like this, that this guy is a colimit of duals of p's. We still need the trace class claim, but I claim that also holds for soft reasons. So the trace class. So there's a general topology fact that if X is a topological space and Z and Z prime are closed subsets such that there exists an open U which lies in between them, so two closed subsets which are separated by an open subset, then the map from the push forward of the constant sheaf, the restriction map is trace class. in the derived category of sheaves. Okay, or really I should say, maybe I should say sheaves on X with values.
Sheaves on X and then?
Oh, with values in D of Z. Yeah.
Which is not the derived category of X in general because it's...
Right. Yeah. So then on the level of just this closed interval from 0 to plus infinity, then any of these transition maps will be trace class for this reason. And then you can pull back, that's a symmetric monoidal functor, you get that they're trace class, you get a trace class map in the derived category of P1, but it lives on A1, and then there's another trick to see that its image under the forgetful functor to the base is also trace class. So there's, so pull back to A1, use another trick. And the conclusion is that the restriction map, say from any of these overconvergent guys, is trace class. And then also for then again by sandwiching different versions of the disks and changing the radii, you also get the, and using the trace class maps as a two-sided ideal in all maps, then you get the presentation like this, which lets you calculate. Do what by hand?
You want to write these overconvergent functions on this disk. I mean, we declare this to use with a piece.
Yeah.
You can just the system and see that each of those transitions is really connected to a PU and this trace dot.
Yeah, there's I believe you can do that. So certainly I remember doing that in the complex case, and I assume it works over the gaseous base too. But I thought it was nice to be able to do it without doing any calculations. Yeah. Okay.
I mean, after having all that stuff, we still need to know that the way you present it is the way you think you present it.
Well, yes, that's true. That's true. Yes.
What was the remark?
The remark was I wasn't being very careful here about writing what the filtered systems are and all this.
Okay, you also saw that it is the...
Yeah. Okay, so what that was a bit of a digression. So what were we doing? I said we were calculating the normed analytic ring structure, and the conclusion was that the norm on spec R gas is given by usual overconvergent functions on disks over R. So that was the conclusion. So then you need to see, well, what were we trying to show? We were trying to show that for this norm here, this universal norm that we produced by fixing the norm of pi, that automatically the norm of every other element is correctly bounded. So to show norm of f contained in 0 f for all f, it suffices to show. It algebraically translates into, oh no, now we have bad notation.
It's not clear a priori that it is finite.
Sorry?
You have to know even the finiteness is a statement.
That's correct, yeah. So we have to show that if you take this and you mod out by t minus f, you just get R. So this.
Okay, this is elementary.
And indeed, this is elementary. So the map giving this is of course setting t equals to f. And it's quite elementary, as Ofer says, to see that you get the correct short exact sequence of Banach spaces. So that the kernel of this map about t minus f is a...
Existence of the map enough?
What's that?
Is the mere existence of the map enough?
Is mere existence of the map enough?
Because it's not about algebra.
Oh, that's a really good point. That's a really good point, Peter. Yeah, thanks. Yeah. So what Peter was saying, so what Peter was saying is that, right. We know a priori that this thing is an idempotent algebra over A1, so over the polynomial ring on one generator. Therefore, when you base change it along here, then you get an idempotent algebra over R bracket T mod T minus F, which is R. So this thing is an idempotent algebra over R, and so is R itself. And if you want to show that two idempotent algebras over R are equal, it's enough to just produce an algebra map between them. Thanks a lot. That indeed makes it very, very. No, just we already have the unit map. Yeah, a map in both directions indeed, but we already have the unit map. So
let's see. Because when you do it analytically, with this, instead of over convergence, just convergence on a closed disk like before, and of course you have a map. When F is less than or equal to C, you get a map, but to prove Weierstrass division, you still get to some convergence, which is not okay in the Archimedean case, and so it is.
But it's not idempotent. It's not idempotent in that case. It's not idempotent in that case. If you don't do the overconvergent one, if you just do the one without the overconvergence, it's not going to be idempotent.
So the argument would not work.
Exactly. So somehow the proof of idempotence is. You must have already done work similar to showing that,
But in the non-Archimedean case, the thing with the affinoid algebras does work.
Yes.
And in this case, the affinoid algebras are idempotent or not?
They are. Yeah. Yes. Yeah. When you do it with the non-Archimedean, everything non-Archimedean. Yeah.
Then why is it idempotent? Because. Okay.
I mean, we basically proved it when we discussed the solid theory, but maybe.
Okay, if everything is not.
So there you can use the
And solid, then it is idempotent.
Right. So, okay, but yeah. So in any case, the map exists because you can evaluate at t equals f, and as Peter points out, that's enough. Thanks, Peter. Right. Okay. So that was the first part of the claim. So that was the claim that this thing is this Berkovich spectrum, this analytic stack, which I'm calling the Berkovich spectrum, is affine when you have that assumption star. And the next claim was that the analytic ring structure is independent of the choice of the norm. So proof continued. Need that spec R gas is independent of norm and pi, say.
Of norm, and that is if you have two topologically isomorphic. That depends on the condensed, the topological.
Exactly.
And without, so you could have one norm with this one pi, which is okay for one pi, another norm which is okay for pi prime.
Yeah, exactly. Yeah. But let me just give the independent description. So claim. So R gas is the initial analytic ring with a map from R triv to R gas, such that, and then we just have a condition, such that for all topologically nilpotent units, pi in R, it's a condition that only depends on the topological ring R. So the R gas is pi gaseous, i.e. that if the map from Z, Q hat plus or minus 1 to R, Q goes to pi, then R lies in the gaseous modules.
No, you need to explain analytic ring structure.
What's that?
So you say it sends level.
Oh, I'm sorry. Thank you. Yes. Yeah. Yeah. Thank you, Peter. Yeah. Not just R, but. Yeah.
Is it enough to check for R, the trivial module, or no?
No, because then you wouldn't have to change the analytic ring structure at all. Then.
Yeah, D of R. D of R is D as a condensed.
D of R is
D of the R of the condensed ring. D of R means.
That should be a box.
No, it's the analytic ring. It's the analytic ring. The R. So yeah. Oh, this should be. Yeah, this should be. Yeah. So I want this to. Yeah. So this map gives a map of analytic rings. The condition is that this map gives a map of analytic rings. To R. And what that condition means.
The instruction on R was what? I forgot.
Oh, sorry. I'm sorry. Let me say R gas is the initial analytic ring A with a map from R triv to A, such that for all topologically nilpotent units, A is pi gaseous, i.e. This map here yields a map of analytic rings like that.
So there is an easier, probably much easier question in this context, which if you have two norms, the same, then the Berkovich spaces are the same. Is it true or not exactly? Because if you have two norms,
yeah.
So since the condition is less nor equal to some, somehow you don't if you're not a topology, you don't control things far away from zero, but because of the unit you can scale. So, but still, I wonder about, at least in the non-Archimedean case, one can compare to Huber and get that it's the same. Because
I think
there's dwarfication. It is dwarfication of some. You can, but in the Archimedean case, of course, there is this in the Berkovich spectrum. There is this condition that.
I think if you take the you could also try to make a modification of the Berkovich spectrum, only thinking of R as a topological ring, where you ask for these semi-norms to be continuous. And then I think if you take that space and then you mod out by this exponentiation action by positive real numbers, then that will be the same as the Berkovich spectrum for any fixed norm satisfying condition star.
No, because but the Archimedean, the Archimedean things,
yes,
you don't, because in the Berkovich space you don't identify a norm to its powers.
Right.
So I don't see how you.
No, but the identification is maybe not so obvious. It's kind of, well, I'm not sure, but.
So you say, because you want to claim that your Berkovich spectrum, of course, it maps to the space, the Berkovich space, as we said.
Yes.
But you don't claim here that the map is, because if you want to claim the map is the same, you have to compare the Berkovich spaces, and this looks like a little bit tricky, at least in the away from the non-Archimedean case, we can understand it. Anyway, I'm not sure.
Well, yeah, I don't know. Right. Yeah. So let me give the proof of this claim, which is kind of giving a intrinsic description of this gaseous analytic ring structure. So note that if pi is topologically nilpotent, then there exists a n such that so we're And after passing to some power, you have small norm. In particular, you have norm less than 1. And let me note that this condition here, this is invariant under replacing pi by any power. This is actually a remark that Peter made at some point early on. So we can assume that pi is norm less than 1. But then for the universal norm we built over R gaseous, sorry, I need to fix maybe, okay, so my claim is going to be, so certainly this R gas that we built it so that it satisfies a weaker version of this property where you only demand it for a fixed pi satisfying this condition here. And what we need to show is that, so R gas was built to satisfy star just for some fixed pi 0. And now we have to show that it's satisfied for all choices of pi. But then can assume 0 less than pi less than 1, and then that implies that the norm of pi is in this interval from 0 to 1, which we already showed implies that pi is gaseous, just from the axioms of a normed analytic ring. Okay.
What is pi 0? Ah.
For R equals Z, what is a Z gas?
It doesn't make sense because I've only defined this when R is a Banach ring satisfying this condition star. Well, sorry. The other condition star about the existence of a pi with norm between 0 and 1, etc.
Pi 0, yeah. No, fixed. Pi 0 is a
it's a fixed. The way I built this was I took my norm and I took a fixed pi 0 satisfying condition star, and then I built my analytic ring and I built my norm over it. And now I want to check that that thing satisfies this universal property, which means that so it was universally built to satisfy that just for a fixed one, but then and to have the correct norm on there. And then I want to argue that it. I want to argue that automatically all of the other possible pi's are also gaseous. And we can use the norm to prove that because the norm is such that it, such that we have this chain of implications. Okay? Right, and then the last part. So the last part is right, that the norm, if you have, so that was the analytic ring structure being independent of the choice of norm on R, but then the so the last part, so this norm on spec R gas, which this a priori depends on is independent of the norm up to exponentiation by a map spec R gas to R greater than 0. Yeah, right. So So let's say we have two different norms. We have n given by this here, and we have n prime given by this here. And both norms have to satisfy condition star, but possibly for different choices of pi. And so this one satisfies star for, say, pi prime. Okay, what can we look at? So again, we can assume that the norm of pi prime is less than 1. So now pi prime had some nice fixed properties with respect to this, but now with this one it's just some arbitrary map to 0, 1. But that implies that with respect to the norm n, that if you take n of pi prime, this is a map from spec R gaseous to 0, 1. And then it follows that there exists an alpha such that n of pi prime raised to the alpha is equal to just the constant value, the norm of pi. Because exponentiation acts transitively, so, or acts simply transitively, so. Uniquely transitively on 0.
N of pi prime doesn't it by definition vector over?
Yeah. So this is the thing we have to. Yeah. Let me finish the argument. Then I think you're probably right. So we'll address Ofer's point at the end of the argument. But then n and n prime are two norms. Norms on spec are gaseous, both with wait, sorry. Norm of pi.
Maybe denoted by double bar prime.
Double bar prime.
I think n prime should be double bar prime.
N prime should be double bar. I don't know. Sorry. So n to the alpha, n prime, yeah, are two norms with. Sorry. I want to actually make this equal to. Wait, sorry. Yeah. Right. Okay. Are two norms with same value on pi prime. So then by the classification of norms, they must be equal. On pi, some value, so same fixed value. So the value is a fixed real number between 0 and 1, and we showed that such a norm is uniquely determined when we proved this classification of norms. Okay. And maybe I wanted to do this or something. I don't know. We can do whatever we want. I forget. Yeah. Yeah. I don't know. Yeah, I think that's right. I think that's what I want to write. Okay. So now to address Ofer's question about whether this map alpha is pulled back from the Berkovich space. So Ofer's question is alpha spec R gas to R greater than 0 pulled back from so this is the canonical map, and then this question is whether there's some map there. To answer this question, we need to answer whether this map is pulled back from the Berkovich spectrum. So true if norm of pi prime is, but that's true by construction. Because the Berkovich spectrum was exactly recording the norms of all of the elements in R, and in particular, we're recording the norm of pi prime. So the answer to your question is yes. It's
okay. Now I see. I understand. I understand. And I think it should be also true that any two choices of norms on your ring are differ by exponentiation to and up to constant, are equivalent in the sense of two constant by anyone is equivalent to some with this constant. I mean equivalent in the sense of bounded ratio from two sides to the power of the other.
In the under conditioned star, you mean?
If you have a ring with topologically important unit. First of all, if you have a topological ring complete, let's say you don't need complete with topologically important unit, then you can see that the topology is given by a norm satisfying what you want.
Oh, is that true?
This is something in general topology where for a uniform space, they construct metrics that give it. But if you have an abelian group, it's enough if you have got a system of neighborhoods of zero, fundamental system that un plus 1 plus un plus 1 containing un, and let us say symmetric, I'm not sure. Then you can decide to make a metric by deciding the elements of un of norm at most, let's say 1 over 2 to 10, you check the metric condition. Here you can do something similar, because if you have a topologically nilpotent unit, and if you have a fundamental I'm not sure if about the countability. My idea is I need to know that it's not only topologically nilpotent, but there is a neighborhood of zero, such that q to the pi to the n times it is converges to zero. So there is some boundedness, some conditional terminology. Okay, then you take u and omega, you replace omega by a power so that I don't know.
Do you work with two equivalents or not?
No, he's not asking a question. He's telling me something, and I want to hear.
So I am afraid that I don't know the conditions that I need. But maybe that there are some but some natural condition in the sense of topological ring that I have to add. I have to take a small neighborhood, open neighborhood, such that the power of so that it times small neighborhood converges to zero, so pi to the n times it goes to zero. Then for some n, pi to the n of it plus pi to the n of it is contained in it, and then you can construct the metric using by replacing pi to the n, and then you will construct at least by construction. I think somehow I force the pi to have norm 1/2 roughly, but then I can probably make it global. Okay, one has to work it out, the details, and then it will turn out that if you have a continuous map to a valued field which is continuous, and the norm of my pi is less than or equal to is 1/2. Anyway, then it will be also less than or equal to this, probably.
Well, it will be equal to 1/2,
Okay, then it will be less than or equal to this. And then, this is one idea, but then if you have got
but by the way, with this construction, you'd get only the triangle inequality, maybe up to some constant again?
No. If I have, what I claim is that this is something that I check. So if you have a non-commutative, I forgot now, if you have got, in general for uniform spaces, they have you need to, they work with 3, but if you have a commutative abelian group, you can do it with 2. So I just claim first that if you have a topological abelian group with topology is defined by a sequence of, let's say, symmetric neighborhoods of the origin, un, so un plus 1 plus un plus 1 is contained in un, then you just get a metric by imposing that the guys in un have norm at most 1 over 2 to the n. So you have a metric in a generalized sense. It could be plus infinity for something. Then I will change it using the unit, I will correct it using my pseudo-uniformizer, but at least I will get, okay, maybe what I'm saying is a bit, maybe I'm thinking too fast with some mistakes. But in any case, I think it will also come out that any two norms are, in some sense, yeah, but this I'm not sure. Any two norms.
Okay, maybe we can discuss later. Let me just finish. I have only one more thing to say, and it's quite short. So, yeah. Right. The last thing is, I want to talk a bit about just say globalization. Only to say that it's trivial. So we could make a definition, I don't know, I mean, it's a definition of Berkovich analytic space, I don't know, is a pair X, or triple, X, S, pi from locale of opens in X to S, where X is an analytic stack, S is a locally compact Hausdorff space, and pi is a map of locales. Such that locally on S for the topology, the open section topology, or the local section topology. It is isomorphic to spec Burke R norm, M R norm, and then this canonical map pi for some Banach ring R. Okay, so this is completely trivial now to globalize, and yeah. So the only point to note is that working locally on S, you're also automatically working locally on X. And that's because these, by definition of a map of locales, a cover in the open cover topology gives a cover in the sense of open covers of analytic stacks here, and those are covers in our Grothendieck topology that we use to define analytic stacks. And there are even open covers in the sense of the six-functor formalism.
Oh, what does mean local section topology?
I mean the Grothendieck topology on locally compact Hausdorff spaces, which is generated by open covers.
Okay.
Yeah.
It is isomorphic to the
issue is that the basic objects have a compact Hausdorff space, underlying space, and so you can say locally is a.
Yeah. So recall that these affine ones are always compact Hausdorff. So you're not going to kind of, if you say locally in the too naive a sense, you're not going to get any examples because open covers, open subsets of say R are usually not compact, right? So, but if you do this usual thing of having a compact neighborhood of every point, then it's fine.
But this looks. I wonder about the derived nature of the R when you localize, because it seems to me that, of course, you can make this definition, but then you can ask whether, for example, what does it mean locally on S? If it is true, if you take just, do you have like for sufficiently fine, for small open, it is, let us say, that if it is true for some cover, it is true for sufficiently fine ones, then probably you have to pass to the ring associated to some small distance. Those are derived in some sense.
We have the same problem we had in general with the discussion of the Huber theory in the solid case. It's the exact same issue, and it's the exact same situation that, yeah, you can fix it by starting with some more general class of derived things here, Well, probably. I didn't think of the details. But also in practice, in most examples, it doesn't show. I mean, in practical examples, it tends not to matter. I mean, in the sense that these you'll have a neighborhood basis. That when you calculate these neighborhood bases, they will just be in degree 0, and the rings will just be in degree 0, and they will fit back in the framework. So you're right that there's a bit of a fly in the ointment in terms of the way we're presenting things, and that we're starting always with classical objects, like when we talked about Huber's theory. And when we're talking about this theory here, we're starting with classical objects instead of derived objects. And a priori, when you work locally on the spectrum attached to our classical object, you see some derived objects instead. But in practice, it doesn't tend to happen. And in any way, you can modify the definitions a bit to accommodate them. So it's not such a big deal.
It's slightly more subtle here is that the basic building blocks that we start with are Banach rings. But then the sheaf of algebras we follow, and there's overconvergence. So it's actually never basically a sheaf of Banach algebras. So there's some kind of mismatch between the global object we start with and...
No, but still, that doesn't obstruct the claim that there's a neighborhood base,
Yes.
I mean, Ofer's question was about a neighborhood base. Yeah. Yeah, that is a good point. And I mean, you can modify these. You could also, instead of these guys, you could also pass to inverse limits. So starting with these affine guys, you could pass to arbitrary inverse limits. For example, so inverse limits in the compact Hausdorff space and just filtered, inverse limits in the category of analytic stacks, which in the affine case is just, filtered colimits of analytic rings. And then these overconvergent things would also count as affine, and then maybe that's a little nicer to work with, and there's no harm in doing that. But
and overconvergent things will not be Banach rings, but they will be condensed rings with certain.
Yeah, they'll still correspond to an analytic stack with a structure map to a compact Hausdorff space and so on.
Okay, yeah. So you probably instead of Banach ring, you can have a condensed ring with certain properties.
Yeah, with some norm satisfying some properties and so on. Yeah, I mean, we didn't try to give the best possible formulation. It was just wanted to connect to the classical thing. Yeah. Okay, so that's all. Thank you.
Sorry, can you say again what is local section?
Oh yes. So on the category of locally compact Hausdorff spaces, you can define a Grothendieck topology where a set of maps. I mean, it's a set of maps like xi to s forms a covering if for every point of s there's an open neighborhood of that point and an index I and a section of the pullback. You pull back xi to that open neighborhood, you should have a section there.
But the map can be arbitrary.
Yeah, the map can be arbitrary. The map doesn't have to be an open inclusion. But it's also the same thing as the Grothendieck topology generated by the covering families, which are just the usual open covers. So if you look at just the usual open covers and say that you want sheaf condition for that, you automatically get sheaf condition for anything, any map that has local sections. So that's so the sieve will always be the same as the sieve generated by some open cover of S, and so yeah. But it's convenient when you want to talk about the sense in which a locally compact Hausdorff space is locally compact Hausdorff, because it's not true in some naive sense, but it's true in this sense. Okay. Yeah. Other questions?
And another question it seems to me that if you take at least naively, if you take another pi prime, then the norm is supposed to be a constant.
N prime of pi prime was supposed to be a constant, but n of pi prime can vary over the Berkovich spectrum.
But I think with all this axiom, it's supposed to be a constant because pi prime is smaller than the normal pi prime inverse. The same, and it's supposed to be actually simply.
No, see the norm pi prime was adapted to absolute value prime. It wasn't adapted to absolute value, so it's not adapted. So this n here wasn't such that it satisfies that property with respect to. So how did we built this n from this absolute value here, for which pi had this property that the norm. So we had, in other words, we had the norm of pi inverse equals norm of pi inverse here, right? And then we built this n using this, so that the norm of every element would be bounded by the norm prescribed here. That implies that n of pi has to be this fixed value. But it doesn't imply anything about n of pi prime, because pi prime doesn't necessarily satisfy this property for this norm. It only satisfies it for this norm.
So it's always satisfied. You have
Okay, thanks guys.